Hello, everyone. It's me, Billy Younger, again. Just want to let you know that I'm going to try to give you an idea of how you might want to motivate or come up with Schrodinger's equation. I'm not sure that this is how Schrodinger did it. A friend of mine, Mark Rupright, gave me the idea, and I like it. So I worked it out in detail and use it for my students. So I thought I'd start with the idea of a plane wave and shoot at conservation of energy and come up with a version of Schrodinger's equation that turns out to be the right one. So this is just what I call motivating Schrodinger's equation. Again, not saying this is the way Schrodinger did it, but it is certainly a reasonable way to make a hypothesis about it. And I owe the idea to Mark Rupright, a good friend of mine. So let's turn on my document cam and get cracking. So it was obvious that basically we were leaning towards a wave type phenomena, but between various things that were going on in the early 1900s when we were developing quantum mechanics. And one way you can write a plane wave, of course, is with exponentials as opposed to sines and cosines. So you might actually take the idea that maybe psi, the wave function, is a standing wave, and you might say that standing wave can be represented by some amplitude times e to the I. And the normal wave function or plane wave scenario is kx minus omega t, which if you've seen any of my other videos, you know that can be generalized to k dot r, where k is the wave vector, its length is 2 pi over the wavelength, and it points in the direction of velocity. X would be replaced by the r vector, which has x I hat plus y j hat plus z k hat. So it points to a point in space. And omega is really the angular frequency or the radians per second. So if we use this as an idea, we might want to think about what about energy? What about kinetic energy plus potential energy is equal to total energy? Well, that doesn't lend itself too easily with this expression. So what I'm going to do is make some arguments about how I can rewrite this in such a way that it gives me something that I can use, and then I will consider derivatives of it because we know if I want a wave equation, typically the wave equations are of the form d2 psi over d x squared plus one, or excuse me, equals 1 over v squared d2 psi over dt squared. That's the normal scenario for a wave equation. So I got to think in terms of derivatives, things like that. If I remember that the de Broglie relationship was P is equal to H over lambda, I could consider dividing that H by 2 pi and then multiplying that 1 over lambda by 2 pi. And then I'd actually get H bar, which is H over 2 pi is defined to be H bar. And I could get K, which is the wave number, and that's defined to be 2 pi over lambda. So that's one thing I could do, and that would actually allow me to replace K times X with something related to momentum. So for instance, I could say from this, K is actually equal to P over H bar. Similarly, I have omega, and I remember from the Planck hypothesis that basically Planck said the energy would be an integer times h times f. So we could use the idea of E equals hf. And this time I am going to again divide h by 2 pi. And to compensate for that, I'm going to multiply by 2 pi times the f. Well, in that case, again, we get h bar, which is defined again by h over 2 pi, and omega is 2 pi f, so that's h bar omega, and that tells me omega is actually equal to E over h bar. With that in mind, I could then change my wave function to a e to the I, and now instead of kx minus omega t, I'm going to say px minus et, all that over h bar, like so. So let me write it a little bigger because I realize now I wrote that so small. What our wave function is going to be is a is equal to e, excuse me, psi is equal to a times e to the I, and then I'll do px minus et, all of that over h bar, like so. Now, again, thinking about the wave function, the wave equation being dependent on derivatives, I'm going to go calculate the derivatives and see what happens. So I first take d psi over dx, and of course the derivative of an exponential function is just the derivative of the exponential to the u power is equal to e to the u power times du dx. In this case, since I'm taking the derivative with respect to x, du dx just becomes I p over h bar. So I'm going to get I p over h bar times a e I px minus et over h bar. And then, of course, the second derivative of psi with respect to x, and these really should be partial derivatives, but it's okay what we're doing here. I'm going to do the exact same thing again, but I already got this constant in front of it. So I'm going to end up having this constant squared. So it'd be I squared times p squared over h squared. And of course, I being the square root of -1, this becomes negative p squared over h bar squared times a e to the I power raised to the px minus et, again, over h bar. So that's the second derivative. Now, if I look at that, I can see, okay, well, p appears to be related to a second derivative. We might even argue from this point that p could equal, if I try to solve this for p, it looks like I would have to multiply by -1 to get rid of that part, and then I'm going to have to multiply by h bar squared, and this will be, of course, p squared. Then I'll multiply that by h squared, negative h squared, that'll cancel out that, and then I multiply that by d, or more specifically, second partial of psi with respect to x squared. You could actually say that maybe p is equal to I h bar partial psi with respect to x. And then, of course, the p squared would be I h bar times I h bar times second partial with respect to x. And that is actually a generalization of the momentum operator, so it actually works. Now, if I wanted to talk about the kinetic energy, and I assume this was really the momentum, we know that kinetic energy, which is 1/2 mv squared, we could actually write that as 1/2 m times p squared. And in case p squared, notice what would happen. That would be a m squared times v squared. So we'd actually want to get rid of some of this stuff. This would become, so I need to leave a space here to make this turns out what it becomes. So I'm going to put the 1/2 m here, and then I'm going to recognize the p squared would be m squared v squared. What I really just want, though, of course, is 1/2 mv squared. So if I really want that to be kinetic energy, I've got to get rid of, in this case, 2 of the m's. So m squared like that. That doesn't necessarily help me out. What I'm really looking for is kinetic energy is equal to p squared over 2m. In other words, I screwed up a little bit here. I was trying to figure out what I had to multiply this by to get that out, and I just went on a terrible tangent. So anyways, the kinetic energy is actually p squared over 2m. So if we want to say the kinetic energy in kinetic energy plus potential energy equals V equals E, like I have there, then I might replace the kinetic energy K with equal to P squared over 2M. And I found P squared was negative H bar squared D2 psi over DX squared. So K should be negative H bar squared over 2M second partial psi with respect to x squared. And of course, if you wanted to go that way in, of course, all directions instead of just x squared, you wanted a three-dimensional one, then you'd take the del squared operator. So it'd be negative h bar squared over 2m del squared psi. So that's really the kinetic energy. Now, if I take the derivative with respect to time, I'll say partial psi with respect to t. In general, the wave equation has, as you see here, as you see here, a second order derivative with respect to time. We may or may not need that, and I'm going to inspect that now. So I'll take the derivative of psi with respect to t. Again, psi is supposed to be a times, or a to the e, a times e to the I, parentheses px minus et over h bar. So when I take the derivative of that with respect to time, I'm going to get a negative ie over h bar times e to a times e to the I, blah, blah, blah. So the first derivative is going to be negative ie over h bar times a e I to the px minus et over h bar, just like that. And from this, you can see, oh, wait a minute, maybe we should recognize E as negative h bar over I times partial psi with respect to t. And if you really wanted to, you could make this multiplied by I over I, the I in the bottom, multiplied by an I would make I squared. That'd be -1. That would cancel out this I. So I could say it's actually equal to I h bar partial psi with respect to t. So that turns out to be an operator that we could use as well. When I go to do this, then my expression k plus v equals E might need to be represented by negative h bar squared over 2m del squared psi plus v psi is equal to I h bar partial psi with respect to t. And it turns out that's actually the correct Schrodinger equation. In the process, we did find that P equals, I normally use h bar over I partial psi with respect to x, or more specifically in the generic sense, the total P for any x, y, z variables is h bar over I del psi. And then you can get the actual momentum out of it that way. And we did find that E operator is I h bar partial psi with respect to t. So these are actually helpful operator instructions. And this is a way that you can come up with a Schrodinger equation on your own just by thinking about plane waves, taking the first derivative with respect to x, taking the second derivative with respect to x, and then trying to look for a derivative that will give you a relationship for E. When you do that, then you actually will see that you get exactly what Schrodinger's equation is. So hope that's enlightening to you. And again, I want to thank my friend Mark Rupright for giving me this idea. Of course, I don't want to blame him for any of this screw up that happened here. So let's just pretend this never happened. Just keep that between you and I. Have a good day.